Okay, in this video, I want to talk about constrained diffusion. And so diffusion is a process where the random movement of molecules causes higher concentrations of some chemicals to move to lower concentration because of their random motion. If you have a lot of them right here and they're randomly moving around and none there, then you'll see a net movement from the higher to the lower concentration. All that is governed by Fick's laws. So Fick's first law says that the flux in that direction is proportional to the concentration gradient. And then the proportionality constant is the diffusion coefficient, which is a property of a chemical in a solution that is related with how quickly the molecules are going to move. So smaller ones will go faster and bigger ones will be slower, and higher temperatures will go faster, and they'll be faster in gases than in liquids. So in this situation, we want to look at a case where we have just random molecular movement in a finite medium or a constrained medium where we have boundaries on both sides. So over here, we're going to imagine that we have an infinite reservoir of or an infinite, what we call an infinite sink here. That is, it's going to stay a concentration of 0 at all times, and over here it will also have an infinite sink. And then we have some mass of this chemical in here, and so over time, any molecules that leave here and hit this one, they instantly get diluted down to 0, and they're sort of escaping from the system, and likewise on this side. Okay, so we're going to imagine we have some initial concentration across this medium, and so our initial condition here, plotting like C versus X, is some function f of x. Okay, and so this, it turns out that it doesn't really matter what this is. We can do most of the work here and then just deal with the initial condition at the end. But we'll imagine for now that it's just a constant value. Okay, so it could go up and down, it could go down and up, it could go wavy. It doesn't matter what the initial condition is. We'll call it f of x, but then we'll do it for that value being constant. All right, so this is the initial condition. And what I want to do before we get into any of the math is to just kind of imagine what we think this is going to look like. So we'll say our expected behavior here is, what do we think is going to happen? So here we've got the distance between these two infinite sinks, quote unquote, is L, and we've got something in the middle, and then because they're both sinks, again, all the molecules that get to the boundary there are whisked away and they go to 0. All right, and this is something that you can set up and actually do something reasonably close to this in reality. Okay, if you have like a thin tube and you've got a big tank over here and a big tank over there, where they're mixed, the mass in here will be really small compared with the outside. So it's not such a crazy thing. So, but let's think about what we expect this to do if we were to make a plot, because we're going to do a bunch of math here. But the math is really just to give us an equation that tells us something that kind of should make sense to us. All right, it should be sort of intuitive at least. And so here we're going to plot, again, concentration versus distance, and I want to look at what this looks like at different times. So we know at the beginning here that's got a value of C0, okay, and then it goes from 0 to L, okay. So we've got kind of a constrained case, and so this is at t equals 0. And then what's going to happen here is as soon as we sort of start the clock and this goes, then the concentrations here, it's really high, and over here it's 0. And so the mass is going to start flowing out on this side, and the mass is going to start flowing out on this side. Okay, and so here it's an infinite sink. That means it has to immediately drop down to 0. And so our kind of very short time, t is like just very small, should drop down like that. And then it takes time for things to get through. So this would be like t equals, 0 plus, and then it should kind of go, more of it over time will bleed out, and you can see that the slope here is getting less. That means there's going to be less movement of chemicals, and so it should go like that, and then it should kind of drop down more, And again, we've got this sort of infinitely powerful sink, and so it should drop down. And then as t goes to infinity, it should drop to 0, okay? So what we want is some kind of crazy equation that looks like this, that has a value that satisfies all of these different conditions, okay? And so the first thing that we need to do in looking at this is a mass balance. Okay, so if we do a mass balance on a differential element, okay, so if we were to look at like a little bitty piece here, then it's going to have some thickness delta x, and there's going to be, it's at some arbitrary point, there can be a flux that comes in, and that flux from Fick's first law is dc dx, and this is at location like x right here, and then here this is x plus delta x. And then this has some area A, and so a mass balance on that one is just, you know, accumulation is going to be in minus out, and there's no reaction here. And so the rate of change of mass in there is going to be the area of this times the thickness, so A delta X, that's the volume, and then times the concentration that's there. And then we're looking at the rate of change of all that. Okay, and that needs to equal the flux in, which is going to be minus d dc dx at x, and that's a flux, so it needs to be multiplied by area, so this is mass per volume per area, and then minus a negative d dc dx at the x plus delta x, so this is like the mass flowing out. And if you rearrange this, so rearrange and send delta x to 0, then we end up with dc by dt is equal to d squared c by dx squared. Okay, this is Fick's second law. And this is our governing equation. Okay, so this is a partial differential equation because it has a derivative with respect to time and derivatives with respect to x. Okay, so this is a second order in space. And it's one dimensional because it's only x. Okay, here we're imagining that this is all happening this way, but it's not coming at us or going up and down. You can have diffusion in those other dimensions, but just doing this. So second order in space, one dimensional, it's a transient. Yeah, so these are, and it's linear, okay, which makes it a little bit easier to solve because these are all just derivatives here. There aren't any products of C together. And so our independent variables are the thing that are the domain that we're looking at, and that's going to be x and t. Our dependent variables are is just going to be C. So concentration is the only thing that changes as I move across space and time. That's the concentration changes, and then the parameters here are the constants in a system that they would vary from one system to another, but there could be lots of different chemicals, lots of different fluids, lots of different distances that you could apply this exact same problem to. And so those are going to be our C0, our length scale, and our diffusion coefficient. Okay, and so these are constants. This is the thing we're trying to get an equation that's a function of x and t, and then it's also going to be a function of these things. But remember, we can treat these as constants when we start doing a bunch of math. Let's see, what else do we need to go over? So this is all the preliminaries. And so it's a second order in space and first order in time. That means that we need two boundary conditions, and we need two boundary conditions and one initial condition in order to be able to solve this. And again, these are all things that should just kind of come out of what we've already stated. But again, because it's a second derivative in space, it means you need two conditions on x and you need one condition on t because it's a first derivative in time. So our boundary conditions, we have two boundaries in this case, 0 and L, and then in both cases c is 0 at that point. So we might kind of formally write that as c at x is equal to 0 at any time greater than 0. Okay, so these boundary conditions will sort of turn on right at t equals 0. We'll turn it on, and they will start to apply just right after that. Okay, so and that should be 0, and then likewise c at x equals to L at any time greater than 0 is equal to 0. And then our initial condition is c at x. So it can be a function of x, and again, there's no reason that this has to be c0 here. It could be, x 4 minus x squared or something, something like that goes this way or wavy, whatever. But so I'll write it we'll just assume it's a function of x, some general thing, and it turns out that we don't have to deal with it until pretty far along. So we'll look at the case where it could be whatever, and then how to manage that later. So c at x, and this is at t is equal to 0. So at the beginning, it's f of x. Okay, so this completely defines the problem, and now it's just a math problem. Okay, so this first video sets up the problem, and then I will talk about how we can solve this kind of problem in the next video.